All right, the next thing I want to do is to do an example which involves the normal distribution. And with the normal distribution, we're going to assume that we have something that's normally distributed here. And so the example that I chose is about the mean birth weight of full-term newborns. And so this is data from the CDC. And so the CDC's found that the mean birth weight of a full-term newborn is 3,400 grams. And that's 7.5 pounds, a little less than 7.5 pounds. And then we're going to assume that there's a normal distribution here underlying this. And we're also assuming that the standard deviation is 335 grams. These assumptions are not real assumptions. These are things that I made up. The birth weights might not be perfectly normally distributed. They might follow what's called a T distribution, which we'll talk about in chapter 9. And the standard deviation I also made up, but just to make the problem work. So we're just assuming that we have those things. Again, remember that the normal distribution is not helpful necessarily because things in nature follow the normal distribution, but it's helpful for reasons that we'll talk about in chapter 7 and 8, and that what's called the central limit theorem. It turns out that if you take a bunch of samples of any distribution, and then you look at those samples are normally distributed. It's kind of a weird thing. It doesn't matter how weird a distribution you start with. When you take samples of samples, you get a normal distribution. And so the normal distribution kind of pops up everywhere because of the central limit theorem, at least as a big component for that. So anyways, so we're assuming that we have a mean of 3,400. We're assuming we have a standard deviation of 335. And then we want to find the probability that a full-term newborn will have a birth weight of at least 2720. And so the way that we could do that, do this is to take 1 minus p norm of 2720. Our mean that we have is 3,400. Our standard deviation is 335. And so if we do this, this will give us our value 0.9788. Okay, and so that's the probability that we'll have at least that a randomly selected full-term newborn will have a birth weight of at least 2,720 grams. Okay, so there's two ways to do this really that I want to talk about. So using R is the first way. And then let me also show you how to do this problem using the table. Okay, and maybe I'll do one or two of these and then we'll go back and talk about the table. For the second part, we want to find the probability that a randomly selected newborn will have a birth weight of at most 3,000 grams. So here we would just do P norm of 3,000. Our mean is 3,400. Our standard deviation is 335, and we get an 11.6% chance. Okay, and then if we wanted to find the probability that a randomly selected newborn will have a birth weight between 2,800 and 4,500 grams, this would be a big number, but we would just take those two values and subtract them. So we would take 4,500 minus 2,800, and this will give us a 96.28% chance. Okay, and so that's how we would do this with R. I think it's just worthwhile really quickly to talk about how to also do this with the table, just so that you're used to kind of interchanging these. And so let's see, let's find, let's go back and find our table here. I might have closed it already. So let's go back and find our standard normal table here. And what I want to do is I want to use R and I want to find the standard values. So what I want to do, for example, let's do 3,000. I think that one would be the easiest. Let's take 3,000 minus the mean divided by the standard deviation. And then that's going to be our Z value. It's going to be negative 1.19403. And so what we're going to do is we're going to look for, we have to round this to 2 decimal places because that's as accurate as this table gets. And so we have negative 1.19. And so again, remember the way that this table works is that you look in the columns for the negative 1.1, and then the hundreds place is determined by which column we're in. So if we're looking at negative 1.19, that looks like it's 0.1170. And so with R, we get a higher degree of accuracy. We get we got 0.1162. And that's because our value was a little bit more than negative 1.19. So if we were to do P norm of negative 1.19, that would give us our 0.1170 accurate to 4 decimal places. That's where this number comes from. But if you were to do P norm of the number that we found, if we were to do P norm of that number, we would get our more accurate 0.116231. Okay, so again, that's how those interact. So you're going to get a more accurate answer for with using R than you would with the table. Okay, and then you can do the same thing with say 2720. So if you wanted to compute the standard value here, you would take 2720 minus 3400 divided by the standard deviation. That'll give you negative 2.029. Accurate to 3 decimal places would be negative 2.03. And so let's look for negative 2.03. That's negative 2.03. So that's 0.0212. And then 1 minus that would be the probability, because again, remember that the standard normal table gives you the cumulative probability. So it's a probability that we have something less than or equal to our z-score. And we want to find the probability that it's greater than or equal to 2720. And so that would be 1 minus, where did the number go? Here, 1 minus 0.0212. So if I do 1 minus 0.0212, that would be 0.9788. That should be close to what we have. Yeah, that should be close to what we have here, 0.9788141. And again, we're going to get more accuracy with R than we do with the table. And again, that's because we have more decimal places with R, right? With the table, we're just kind of stuck with using tenths and hundreds. We have 2 decimal places. But with our table, we can do a little bit better. Okay, so we can be a little bit more accurate there. The last thing that I want to do, and I should add this to the list of problems to talk about. Let's say that I want to figure out how many. So let's say I want to figure out what's the weight up to which 75% of the babies will be born. So in other words, I want to figure out the 75th percentile of weight. So I want to find the probability that a randomly selected baby will have a 75% chance of having this weight or less. And so if I want to do that, what I would do for this problem is I would use the Q norm. And I'm going to put in 0.75. Remember, our mean is 3,400. Our standard deviation is 335. And so it looks like 75% of the, if you randomly select a baby, there'll be a 75% chance that their birth weight would be 3625 grams or fewer. Okay, and so that's what the Q norm function does, is it answers kind of the inverse question. If you want to know, if you already have a probability and you want to know what's the cutoff for that probability, that critical value, then you would use the Q norm function. So again, 75% of the randomly selected babies would have a birth weight of 3625.954 grams or fewer. Okay, that's how you would interpret that question. Okay, but hopefully that covers everything we need about the chapter 6. So the Q norm and the P norm codes.